So as you know, an atom consists of a very small nucleus where most of the matter and the positive charge lies. But the atom itself is really a cloud of electrons surrounding this nucleus, and the properties of atoms and molecules have nothing much to do with what goes on inside the nucleus. So for the 50 preceding years, we had developed a theory of atoms and molecules based on quantum mechanics, which underlies our understanding of ordinary matter. But until we started constructing large accelerators that collide protons together and allow us to probe matter at very short distances, we really had no understanding of what went on inside the nucleus, except that the nucleus was made out of protons and neutrons, but what protons and neutrons were made out of, we didn't understand. So in this next 50 years, we truly identified the fundamental constituents of matter, which, in addition to the electrons, consist of quarks. We understood that the nucleons were actually composites of quarks, particles that had never been seen in isolation, were kind of weird, but they do make up the nucleons, 3 quarks per nucleon. What I want to stress, however, is the most interesting part of science, in my opinion, is not so much what we know and have learned, proud as we are of these achievements of 50 years, but rather the questions that remain open, the new questions we ask. That's what drives science forward, motivates young people to go into science. It's the unanswered, open questions. That's what defines the frontiers of science, what we don't know. So I provocatively like to say that the most important product of knowledge is ignorance. This is supposed to catch your attention and say, what do you mean by that? And of course, by ignorance, I don't mean the ignorance that leads to bigotry and racism. What I mean is informed, new questions that can be answered by observation, by experiment, and by theory, the scientific method. What I mean is when I started doing my research, there were many wonderful, interesting questions like, what goes on inside the proton? What are the laws of force? What is the proton made out of? Those are wonderful questions. Those questions have been answered. But in answering them and having answered them, we're now smart enough to be ignorant in new ways. New questions arise that we didn't know enough to even ask 50 years ago. And that's what drives science forward. Informed ignorance. You see, in this history of the universe, there's some place where things are kind of fuzzy. Somehow the universe began. The universe is expanding. If we run the movie backwards, which we can do in 2 ways. One, as theorists, we can take our knowledge and make time run backwards on pencil and paper. But 2, we have another way looking into the past to see what the universe looked like, and that is looking at light that has come from so far away that it had to originate 13 billion years ago. And we actually have the baby picture of the universe. A picture of the universe the way it looked 13.5 billion years ago, and here it is. If you look at the right spectrum, the microwave radiation coming from very far away, it's been traveling for 13.5 billion years. What you see is a picture of the universe shortly after the beginning, whatever that is. And it's a pretty boring picture. There are no features. You can't see any nose, mouth, anything. It's in fact almost a perfect hot gas with no structure. The only thing that defines it is its temperature. In fact, it's the most pure black body object created. We can't get something as pure in the laboratory. In the theory of quantum chromodynamics, this is what happens when you pull quarks apart. You see there are flux lines, lines of force, very much like in electricity and magnetism. But in electricity and magnetism, these lines would go out. You know, you've seen these lines of magnetic force field lines. But the quantum vacuum pushes them inwards to form a kind of flux tube, a fat string. And because of that, there's no way of separating the quarks. It would require an infinite amount of energy to separate quarks, which really is the explanation for why no one has ever seen a quarks, even though they're there inside the proton and inside other particles. And it also explains why the force gets weak at very short distances. And that led me to Stockholm. I wanted to show you this because you see the king giving you a bunch of things here, a medal and a check and a beautiful document which has a picture with a picture drawn by a Swedish artist here of 3 quarks, different colors, bound by the strong force, unable to get out. This is what it actually looks like if you do the calculation. Try to pull the 3 quarks out of the proton. Well, I'd like to finally talk about more ordinary physics, or condensed matter physics, atomic physics, molecular physics, in answer to a question which might arise. It's all fascinating, wonderful, but you know, especially as Singapore is a very practical society, what is this good for? And I'm sure many of you have heard about Faraday's answer. Sir Michael Faraday, who is the guy who really discovered the basic phenomena of electricity and magnetism, his answer to Queen Victoria when she visited his laboratories and saw all these marvelous magnets and electromagnets. And she said, "All very interesting, Mr. Faraday, but what is it good for?" And Faraday, of course, had no idea. He didn't know what electricity and magnetism would be good for. He didn't know about motors or currents or electrical lights or the Industrial Revolution. He really didn't. He was just having fun and trying to understand, you know, electricity and magnets and their connection. So he said, "I don't know, but when we find out, you will tax it." So what is this all good for, this theory of the nuclear force, or our even more ambitious studies today? I don't know either. No one knows. The most fundamental research that leads to the most fundamental advances in technology is never or rarely discovered as an answer to some given project of some government or corporation. And the best example by far in recent times is quantum mechanics. Quantum mechanics is this weird new way of looking at the world that was invented to understand how atoms worked. Now, those people who invented quantum mechanics could have thought of applications, but they would not have dreamed of what we've done with quantum mechanics. Planck and Einstein and Bohr and Heisenberg and Schrödinger and Dirac. Quantum mechanics is about nearing 100 years old. It's about 90 years old now. And it totally dominates modern technology. The uses of quantum physics are manifold, from transistors to lasers to integrated circuits and many more, superconductivity. All of our modern gizmos and much of our technology is now based more and more on our understanding and ability to control quantum physics. So even atomic physics, molecular physics, physics of ordinary matter is, although the basic laws are well understood, the understanding and control in a serious way, in my opinion, is just beginning. The prospects for the discovery of new matter and the creation of new forms of old matter are extremely exciting. Some people say physics, the 20th century was the century of physics. 21st century is the century of biology. Well, to some extent that's true. Biology is a very young field. Many of the basic phenomena and applications are just around the corner, no question. But in the end, even biology is really physics. It's the physics of living matter. And there's no question, in my opinion, that physics will continue to be very important, and the best is yet to come. Thank you.